So maybe some people cannot make it, they can watch this recording later. Okay, thank you for your response. Anybody has any questions? I have posted some necessary material on Blackboard. Anyone has any questions regarding grading policy or content to cover or anything related to this course? Let's see. Okay, basically announcements, right? So any correspondence I will post on announcements. So one very important thing I need to tell you is the final. You know, what's included in final, basically everything. So final is accumulative. But when and where, I don't know yet. So whenever I have the information, actually, as you know, as soon as I have the information about final, I will post here. You know, I will make announcements and I will post on course documents. Let's see, grading policy is attendance 20%, classwork, homework 20%, midterm 20%, and final. Final is in person. So final will be on campus, so another 40%. Let me see if anyone has any questions. No, midterm will not be in person. Midterm will be online. Only final is in person. Yeah, this Friday, the department chair, Jeff, will host a meeting talking about how are we going to assign the homework. So for now, each class, I will assign some classwork. And if you cannot finish during class time, then I will treat them as a homework. You do not need to submit your homework before my open math system can be set up. All right. So after this Friday, by next Tuesday, I should be able to tell you exactly what to do with the homework, because the meeting is on this Friday. Yeah, approximately, right. The midterm will be on my open math. So final is in person. Okay, any other questions? The textbook I posted here is just for your reference, because before, that's before I had this account in my open math. But now, since I have my open math, so I'm going to follow that. I'm going to follow, let me share that with you. So this is the homework, not homework, what I'm talking about, the textbook. Okay, it's on my open math. So it's this one. So table of contents here. And chapter 1, let me see if I can. Right, chapter 1, integration. Then chapter 2, applications of integration. Chapter 3, techniques of integration. We're going to skip 4. Okay, 4 is not on the syllabus. Differential equations. So we're skipping chapter 4. We're going to cover chapter 5, sequences and series, then power series, then parametric equations. Maybe it's not heavily covered, but polar coordinates. Where can you find? Let me see, can I start from the very beginning? I should be able to. So let's try to start from the very beginning. I'm going to close all this. Oh no, under course documents, the textbook is like a classic one from Stewart, but for this course, we're going to follow this. Let me just show you. Let me show you where to find it. Oh, I need to open it. I need to open that. Once you log on my Open Math, go to your home, you add your course, okay, like this, right? Enroll in a new class. So you need to enroll yourself into the class. And the course ID and the enrollment key are posted on Blackboard. So once you enroll yourself, you should be able to see Spring 2022 Math 1206. You should be able to see this course. Then you click into it. You see this is everything about this course. You see the lectures, right? You can watch those videos. This is from Department Chair Jeff, right? And the textbook, we're going to use this one. We're going to use this one, all right? A calculus test. We're going to use this one. Okay, any more questions? The textbook and the Blackboard course documents is just a classic one, okay? You can use as a reference now. All right, so my plan for today is to cover chapter 1, section 1, 2, 3. So we're going to talk about approximating areas under a function. And we're going to end up with the fundamental theorem of calculus, which is a very, very important theorem to use. We will use it in integration all the time. If you have any question, feel free to stop me anytime, all right? Oh, hold on a second. Why this doesn't go? I need to get it out of here. Oh, it's here. Which one is this? Let me close this one. Can you see it? Oh, you still see this one? Interesting. I need to reshare my. Okay, now you see it. Okay, so integration. Let me see. I want to make this a little bit bigger for you. Okay, this looks better. All right, a symbol is called a sigma, sigma summation sign. That's this one, right? So what does this sign mean? This sign means add up 1 to 20. So on the bottom here, so in the middle, like a 90-degree M, you know, it's turned 90-degree M. It's called sigma. It's a sigma notation. So sigma notation means a summation. Sum up all the terms. So the variable here is I. We say I is a variable. Then I starts from 1, 1, 2, 3, 4, 5, those natural numbers. Then ends up at 20. Okay. When we use summation sign, we always use natural numbers. Natural numbers means counting numbers. Counting numbers, when you use to count how many things, right? Counting numbers. So 1, 2, 3, 4, 5, so on and so forth. And so this sign means exactly this. Add up the numbers from 1 to 20, the natural numbers. And that's this notation. Well, in this notation, it just means the variable is still I, some AI. You know, A, we don't know what A is in this case. I means from 1 to N. That means A1 plus A2 plus A3 up to plus AN. Let's look at this one. Similarly, this means the I, the variable I, start with 2. So that would be S2 plus S3 up to S7. Right. So this is called index. So this I is called index. The index, you can start with 1, 2, or sometimes even start with 0. You can start with 0. The natural numbers plus 0 means whole number. So the index can be represented by whole numbers. So whole numbers means the non-negative integers starting from 0, 0, 1, 2, 3, so on and so forth. So let's see this one. Using sigma notation, A written in sigma notation and evaluate the sum of terms 3i for I from 1 up to 5. So when I is 1, we get 3 raised by 1, right? This is 3. When I equals 2, we get 3 raised by 2, which is 9, and so forth, so on and so forth. And B read the sum in sigma notation 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25. And we look at this, we see 1 is 1 square. 1 over 4 is 1/2 square. So 1 over 9, that's 1/3 square, so on and so forth. Right? So we observe the pattern. Let's see the solution. So 3 raised by I goes from 1 to 5. That's this. That's the 3 raised by 1 plus 3 raised by 2 plus 3 raised by 3 plus 3 raised by 4 plus 3 raised by 5. And adds up to be 363. Can the index I be negative? No, we don't use negative. We use whole numbers. most of the time we use natural numbers, counting numbers. And sometimes we can start with 0 plus counting number, called whole numbers. No negatives, we don't use negatives. But you know what? All these are by convention, right? If you think negative are useful, you know, maybe you can do something else. All we talk about is basic mathematics. If we talk about abstract, pure mathematics, because so far, the mathematics we're learning is applicable to life. And if you study pure mathematics, that's B, Shin, right? When you study pure mathematics, of course, you can use negative numbers. You can even use irrational numbers. All right, that's good thinking. But at this moment, you know, we were trying to use in life. So we're not learning pure mathematics. We're learning discrete mathematics or, you know, applicable mathematics, applied mathematics. Good question. So that answers A, all right? So that the answer to A is this. So we add up all those numbers, we get 363. B, we observe the pattern. We see there's 1 squared plus half squared plus 1/3 squared, so on and so forth. So the variable is in the denominator, right? So the index still starts with 1 up to 5, because the last one is 1/5 squared, right? So 1/2, 1/3, 1/4, 1/5 squared being squared. So I have this. So we have 1 over I squared. And I goes from 1 up to 5. Okay, anyone has any questions about this? All right, pretty direct, right? Well, if n is constant, if c is constant, this is obvious, right? We just add up n of c's. So the properties of sigma notation, right? If c is a constant, which means c is just a number, you know, has no variable. It has nothing to do with the index I. It doesn't depend on I. So c is a constant. And we just add up n of c's. This is n times c. If we have a constant inside the summation, and we can factor out, because c will be a common factor of every term, right? CAI, so CA, we have CA1 plus CA2, so on and so forth, plus CAN, and every term has a C in it, so C is a common factor. That means we can factor out the common factor C. Then, outside the summation sign, we can just add up AIs, A1 up to AN, then multiply by C. If the summation sign has two sums, it's a sum of two things or sum of finite things, we can split them, right? We can summation each one and add them up. The same for subtraction, right? Inside the summation sign, if the subtraction sign is inside the summation sign, we can split them. We keep the subtracting sign. And of course, if the index goes from 1 up to n, you know, sometimes maybe we need to split into the index goes from 1 to m. M is a number between 1 and n. Then go from the index I goes from n plus 1 up to n. Right, so those are the properties of the summation sign. Okay, we don't. You can look at the proofs yourself. It's very direct. Do we have to memorize all those? Oh, you don't have to memorize it. You just, gradually when you use it, it comes naturally. It comes naturally from 1, it's about the sum. Yeah. Because this is just summation, the sum. Summation sign is the addition. So all those properties come from addition. Because this sigma notation is just summation, just addition. So all those comes from addition. It comes naturally. You don't have to memorize it. But when you do enough time, it just become part of it. Right? You can see this proof. This is very obviously, right? Summation sign, summation of CAIs from 1 to n. Just add up CAI up to CAN. And C is a factor of every term. C is a factor of n terms. So just factor out. So C becomes a common factor. So C is a common factor. So we can factor out C. Add up all the AIs, then multiply by C. That's why C can be written outside. Same thing, this one. We add AI plus BI from 1 to n. It's the same as we add AIs, then we add BIs, then we add them together. Okay, you may want to remember those. Those are good to remember. So those formulas. So let's see the first one. The first one is a very famous one, right? It has a story. Gauss, the greatest mathematician Gauss, when he was 6 years old, he figured out this. His teacher asked him to add from 1 up to 50, and he used no time to give the answers. So that's because he used this. When you want to add all the counting numbers from 1 up to a certain number n, the formula is just n times n plus 1 divided by 2. You could try this on your own to add 1 up to 50, right? 1 up to 50. So you add 1 up to 50, that would be 50 times 51 divided by 2 will give you 5050. Because basically pair them up, right? And this one is a square. That's just adding natural numbers from 1 to n. And the second one is adding the natural numbers squares. And the formula is n times n plus 1, very similar to the first one. Then times 2n plus 1 divided by 6. N times n plus 1 times 2n plus 1, then divided by 6. Why dividing by 6? Well, that's from the proof. We have to see the proof because it's a square. It's a square. The third one is cube. You add the natural numbers being cubed, 1 cube plus 2 cube up to n cubes. The formula is n squared times n plus 1 squared divided by 4. Divided by 4. If the second one and third one difficult to remember, at least you should remember the first one. Okay, the first one is very easy to use. Adding up the counting numbers up to n is n times n plus 1 divided by 2. Okay, let's see this example quickly. So we want to add up the sum. So A, we want to add up the sum of terms I minus 3 squared for I equals to 1 up to 200. Well, let's just put that in the summation sign. So I have summation sign. The index goes from 1 up to 200. right? So the index I equals to 1, put on the bottom. We just jumped, right? So it goes I equals to 1, put on the bottom. Then on the top of sigma, write down 200. Then we want to find I minus 3 squared. I minus 3 square, that's a perfect square. Remember the perfect square formula? Square the first one, which is I square. Square the second one, negative 3 square is positive 9. Then multiply the first one and second one, then double it. So 2 times negative 3, that's negative 6. Negative 6 times I, negative 6I. Right? That's perfect square formula. Then, by the property, adding and summations, adding or subtracting, we can split the split. So that means we can add up t squared, then subtract, add up 6i, then add up to the summation of 9. I squared, we have the formula, right? We have n times n plus 1 times 2n plus 1. So n is 200. N is this top number, 200. Right, this is n. So n times n plus 1, 200 plus 1, times 2n plus 1, well, 2 times n is 200, that's 400 plus 1, then divided by 6. We just follow the formula for t squared. Then for the second one, we can factor I, 6, because c is a common factor. Right, factor 6, we add up i's from 1 to 200. Again, we use the formula. The formula n is 200, so n times n plus 1, 200 times 200 plus 1, divided by 2, then multiply by 6. And last one is 9 is a constant. Remember, if this is constant, it doesn't depend on I, so we just add up 200 times 9, Cn, right? So 9 times 200. Then we calculate each one, we add them up. Pretty direct, right? Any questions? It's just a short notation for summation, okay? Instead of writing, 200 terms, we could use this short notation to write. Let's say B. B, we want the index goes from 1 up to 6. Index goes from 1 up to 6. And inside the summation sign, we need to calculate I cube minus I squared. So we split them again. We summation of I cube first, then subtract summation of I squared. We use the formula. So n squared times n plus 1 squared, n is 6. So we have 6 squared times 6 plus 1 squared, then divided by 4. Then subtract. For the square term, that's the first one is a cubic term, second one is square term. With n times n plus 1 times 2n plus 1 divided by 6. So we have 6 times 6 plus 1 times 2 times 6 plus 1 and divided by 6. We calculate that, we get 350. Okay, anyone has any questions about these summation signs? Okay, notice that these are all finite terms, right? These are all finite terms. Let's see this one. So you want to add up this I cube. Well, So here, what's the difference here? Difference here is we want to find the sum of the values, the function values of f of x equals x cubed over the integers 1 up to 10. Now we do the same. We do the same. So 1 cube plus 2 cube plus 3 cube up to 10 cube, right? So nothing is special for this one. Well, how do we add this one? We use the formula, right? We use the formula. Here we have 2k. We do summation of 2k from 1 to 20. Then add a summation of 1 to 20 of ones. So I'll let you try this. I'll give you 5 minutes to do this. Okay. Let's see what answer you can come up with. Okay, I'm going to take a picture of that for attendance. So this class, I'm supposed to have 35 students. There's only 20. As you have your answer, type in the chat. Four hundred 440. Let's see. So 20 plus 1 divided by 2, 200, right? 220 times 210 times 2, 420 plus 20, 440. Yes. Okay, great. Yes. Okay, so we get this. Anyone has any questions for this? Do we have to bring a calculator for the final? That's a good question. Calculator. Right, if you think you need a scientific calculator is always allowed. But I'm not quite sure about the graphing calculator. All right. Okay, thank you. Now, let's talk about approximating area. All right, so the above just use a summation sign to approximating some numbers. So what do we want to do? Let's see, we have a certain shape like this, right? So 3 sides are straight. So the 2 vertical sides are straight. And the bottom one are straight. Just imagine this is just some shape, right? Some shape. We want to find the area of this shape. The algebra we learned won't be able to do this, right? We know how to find the area of a rectangle, area of a square, area of a parallelogram, those like a regular gongs. We can even find the area of a circle. But with a weird shape like this, we won't be able to find its area by using algebra. So what do we have to do? We have to use calculus. So how do we use calculus? We put this shape on the coordinates, right? We have x, we have f of x. So the horizontal one is x, the vertical one is f of x. Okay. Then we're going to take the top. We're going to see the top part is, it's not straight, right? So that's the part it prevents us from using algebra. So what do? We're thinking this one as a function, right? So this one is a function. So this curve, right, f of x. So we call this f of x. Then we want to find the area of this guy by finding the area under this curve. Under this curve. So how do we do it? We can approximate. How do we approximate? We do this. We slice it. We slice the area. Okay, this is a different shape now, but basically you can think we slice this, right? We slice into certain equal parts of it, just like this one, right? If we want to find the area under this curve, under this function, from A up to B, we just slice, we just making certain slices, right? So here we sliced into four parts. The width is the same. So from A to B, so B minus A divided by 4. That will be the width of each rectangle. So we see 4 rectangles here. And we know how to find the area of the rectangle, just the width times length. So the width we have now, B minus A divided by 4. Right? So we slice into 4 parts. But how do we find the length? So that's the approximating part comes from. So we can choose a point. Here, we can choose the first rectangle. We can choose x0 to be the height, to be the length of the first rectangle. Or we could choose, let's see, I have 1, 2, 3, 4, 4 red points here, right? I can choose the first red point to be the length of the first rectangle, right? I can choose the second one to be the length. So f of a, basically so the function value, right? The function value, the y value. So that's f of a. So f of a times a, times b minus a divided by 4. The width is b minus a divided by 4. I won't be, you know what? The bad thing about this, I cannot write on it. So the width is b minus a divided by 4. And the length, the first one, f of a. So the area of the first one will be f of a times b minus a divided by 4. And the second one, I can choose this. So the second one will be a plus b minus a divided by 4, if you can see that. Right? Or we can call this x1. Call the second red dot x1. The first one, a, we call x0. So x1. So this one would be the length of the second rectangle will be f of x1. Then multiply by the width. So on and so forth. So by this way, we can approximate the area of this one, but won't be exact, right? So if we want to have more fine approximation, so we will divide it into more parts. So here we divide it into 4 parts. Maybe we can divide it into 40 parts. That will be more accurate, right? That will be more accurate. All right. And also choosing x0, x1, we have a choice about that. So which function value should we choose? So here is one way, where we choose a. We choose a to be x0. Then the second one will be x1, x2, x3. Or we can choose this one, right? This first red dot to be x naught. The second red dot to be x1, then x2, x3. And we see the difference. Choosing the point on the right-hand side of the rectangle, the area is more than the actual area. And this one, choose the point on the left, you see the area will be less than the real area. So that's why it's just approximation. And we can split more parts to be more, accurate about the approximation. But it still is approximation. Well, let's see this one. So use both left endpoint. So we want to use the left endpoint. So the first one will be left endpoint. So here, this picture, we're choosing the left endpoint, right, to evaluate the function value. So if f of a is the length of the first rectangle. But here we choose this one. Right? We choose this one, is the first red dot, the right endpoint, the right endpoint. So we would approximate this function value. We would do f of, we would call this x naught, f of x naught, or f of x1 to be the length of the first rectangle. So we have a choice. Sometimes we choose a middle point, right? So middle point, so we could do left point approximation, right point approximation, or middle point approximation. So we have a choice. Let's see this one. This one we want to use left endpoint and right endpoint approximation to approximate the area under the curve f of x equals x squared on the interval from 0 to 2. And we want to separate into 4 parts. Let's see, what do we do? So the endpoints is 2, so a, b is 2, a is 0. So 2 minus 0, which is 2. 2 divided by 4 is 0.5. 0.5 will be the length, the width, right? The width of each rectangle. So the width of each rectangle. And now we want to use, let's use the left endpoint to approximate. So from 0 to 2, if we use the left endpoint, we will have 0, 0.5, 1, 1.5, right? So we will approximate like that. So we do f of x naught, which is f of 0, right? F of 0, because we're doing left point starting with 0. So we 0 times 0.5. The second one will be 0.5 times 0.5. Then third point will be 1 times 0.5. Then will be 1.2. So this is a mistake. It's not 2.25. This should be 1.25. 1.25 times 0.5. So this is typo. 1.125 times 0.5. Add up, we get the area is 1.75. Okay, so this is how we estimate the area of an irregular shape. So we're treating the irregular side as a function. We try to find the function underneath by approximating the rectangles. Okay, anyone has any questions? All right, so let's see. I'm not going to literature. You can practice this on yourself, but I don't think we have enough time to do that. So imagine a shape like this, right? Like an irregular shape. We can put under the coordinates and think about finding the area under the function. Yeah, we can split more rectangles. We can split the area into more rectangles to be more exact. But all those are like finite, right? Finite world. And if we want to do more exact, right, you can enlarge the size of n, right? Dividing into 4 pieces, 4 rectangles, dividing into 8 rectangles or 32 rectangles. Of course, the area is getting more and more accurate. So what is the idea of getting more and more accurate? Come to calculus, right? Limit. We want to divide the rectangles into infinitely more. So from finite world going to infinite world, right? So what do? We use the limit idea. We said, okay, we want to sum up 1 to n pieces of rectangles, right? Then we let n goes to infinity. Let n goes to infinity. In this case, what are we getting? We're getting exact area of the irregular shape. And we call this integral. So the area under the function, if it's a function, it has to be a function, right? The area under the function f of x on the interval from a to b is this. It's a limit, let n goes to infinity. So first we cut into n pieces, right? We add up the n rectangles, but then we let n run into infinity. Okay, that's the beauty of calculus. So make sure if you want to remember anything that's for today, you have to remember this. And in this case, that's the, choosing the point, left point, right point, left endpoint, right endpoint, or middle point, important? Not important at all, because we're taking limit into it. So this function is to find the exact area. The idea is, yeah. So the idea comes, so why do we want to do this? The idea comes from, if we have an irregular shape, how are we going to find the area of something like this? So later on, we're going to talk about, more irregular shape. And for this one, just one side is being irregular, not straight. The other 3 sides are straight. So how to find the area of this irregular shape? We can put it on the coordinates and trying to cut it into rectangles, then approximate these rectangles. And how many rectangles should we cut? We cut a finite many, then we let the finite many, by using the limit idea, becomes infinite many pieces. So because we can cut into infinite many pieces, we can find the exact area. That's the beauty of calculus. All right. Okay, so this is important. All right, so this is the definition. The area under a function, under a curve, under a function, on an interval from A to B. Okay. What's delta x? Delta x is b minus a divided by n, right? Delta x is the width. It's the width of each rectangle. It's b minus a. B minus a. A is the left endpoint. B is the right endpoint for the shape. B minus a, because we're cutting into n pieces of rectangle. So b minus a divided by n, that's delta x. Well, what's f of xi with a star? That means at a certain chosen point. So this xi star is our choice. You know, we can choose a left endpoint or right endpoint or middle point to approximate the function value. Okay, add up all those n pieces, rectangles area, then let n run into infinity. In this case, we can get exact area of the, you can get exact area. Okay, any questions regarding this formula? This is important. All right, so that's the definition, the area under the curve or under the function. Well, let's see this one quickly. Find a lower sum, well, upper sum or lower sum. What is the lower sum, upper sum? This is the upper sum, right? Because the area is being approximated more. If the area being approximated less, that's lower sum, like this one, right? This one, we're using the left endpoint of each rectangle to evaluate the length. If we use the right one, that will be more. The area will be, you see this one, we use the right endpoint of each rectangle. So the area is more. So that's why we call lower sum and upper sum. So we want to find the lower sum for the area under this function, 10 minus x squared, from 1 to 2. And we want to cut into 4 pieces. Well, let's see this quickly. So 2 minus 1, so a is 1, b is 2. So b minus a, that's 2 minus 1, which is 1, divided by 4. So the width of each rectangle is 1/4. And the length we can approximate, right? Starting from 1, so it'll be 1. The first one will be f of 1, then f of 1 1/4, then f of 1 1/2, then 1 of 3/4. So this we're using left endpoint to approximate, right? Like this. So we will have, so this is delta x, 0.25 or 1/4, right? It's the width of each rectangle. The length we are approximating, so 10 minus x squared, 1.25 squared, or so on and so forth, right? In the end, we get a number. That's the area. That's the area. But this area is a pure math area. Okay, no units. We don't care about the units. So this is similarly. Let's see this one. Find lower and upper sum for f of x equals sine x. Right? From interval, so interval a to b, 0 pi over 2, and n is 6. So sine function from 0 to pi looks like this, and we want to find area. Lower sum is from 0 to pi over 2. We do the same, right? Because we're dividing into 6 parts, so we do pi over 2 minus 0 divided by 6. So the width of each rectangle is just pi over 12. Then we have sine of 0, the function value, right? Sine, the length, sine of 0, length times width, length times width, so on and so forth. Then add them up. All right, let me see. Should we do this? Actually, all of those are not so important. So let's quickly go. How I'm gonna get rid of this? Get out of this. Oh, I need this. Yes. Okay, that's about approximating areas. All right. So what's important is the definition of the area under a function, area under a curve, which is this formula. So in this formula, we have a width of, so we're basically under the function, we're cutting into n pieces of rectangles. We're approximating the area of each rectangle, then we add them up. Then we let n run into infinity, which means we're taking the limit of infinite many pieces of rectangles, the area of rectangles, we add them up. Now, we're going to call this area under a curve. We're going to define a new definition we call definite integral. Okay, because this, if you look at this the right hand side, look at the equation on the right hand side. It seems like a and b not there, right? So a and b seems not there, but remember delta x equals to b minus a divided by n. All right, I cannot write here. If you could write a delta x for yourself, write b minus a divided by n. Otherwise, it's easy for you to forget about it, because when you look at this, you don't see a and b, right? You don't see a and b, but a and b is included in delta x. Delta x equals to b minus a divided by n. And the area under a function, and from now on, we're going to call it definite integral. Okay, definite integral. Of course, under the condition that limit exists. Right? If the limit does not exist, we won't be able to make this definition. So the limit exists. If the limit exists, we're going to call this definite integral. Right? Do you see the miracles here? From a finite world. Now, by using the idea of limit, right, we got ourselves into an infinite world, which no humans really understand, but it works. Okay, so that's the beauty of this stuff. And how do we write it? We write it like this left-hand side, the integral sign, like elongated S. Right? It's like you make an S long, you stretch S. You stretch the letter S, right? Then you write the lower limit, A. That's the boundary, AB. A now in this we call lower limit. So this is the integral sign, the elongated S is called integral sign. And the A is lower limit, B is upper limit. So those are the names. So integral sign and the dx is a pair. So the elongated sign of elongated S, so the stretched S with the dx is a pair. And the f of x is called integrand. It's called integrand. So let me write in the chat. So f of x inside the sign so f of x inside, f of x is called integrand inside the integral sign. Okay. The integral sign is the stretched S and dx. Okay, so those two makes one sine. And of course, with lower limit and upper limit. Sometimes we don't have a lower limit and upper limit, but sometimes we do have. So without lower limit and upper limit, it's called infinite integral. With lower limit A, upper limit B, we call definite integral. So this sine and dx is a pair. Dx, you see where does dx come from? So this is delta x, right? This delta x on the right-hand side. So this delta x is in a finite world, right? It's still in the finite world. But dx is the infinite world. The dx is the infinite world. So dx. F of x is called an integrand. And how are we going to do this? I hope you still remember anti-differentiation. Right? We differentiate, right? Differentiate a number, which is the differentiation is 0. Differentiate x is 1, but now anti-differentiation is the opposite, right? I hope you still remember that. Remember them. Anti-differentiate 1, that's x, right? Anti-differentiate x, that's x squared divided by 2, so on and so forth. So by doing this, we're going to anti-differentiate f of x, right? Okay, we'll see that. So this is important formula. This is important definition. So, you know, the beauty of mathematics is hidden in this equation. It's just so beautiful. From a finite world, jump to infinite world. And we're able to find, you know, the area of weird shape by doing so. Okay, anyone has any questions? All right. And the variable wise, yeah, the function, the variable in the function has to be aligned with the dx. You see, this is dx, right? X dx, or t dt, or u du. Okay, they have to be aligned with each other. Sometimes if they're not aligned, let's say f of x dt or something, in special situations, and we're going to see that. So in the definition here, we see, okay, function f of x has to be integrable functions, right? So what is an integrable function? It's a pure mathematics idea, but all we have to remember is continuous functions are integrable. That's it for us, all right? If a function is continuous on the interval a, b, that means the function is integrable. That's all we have to know. Okay, let's see this one. Evaluating the integral using the definition. So we want to find integral from 0 to 2 x squared dx. All right, we want to use the definition. Right, remember the definition. We take a limit that n runs to infinity. So find the delta x first. Delta x is b minus a divided by n. Right. Here, what's our, from 0 to 2. You see the lower limit is 0, upper limit is 2. So a is 0, b is 2. So we want to do 2 minus 0 divided by n. 2 minus 0 is 2, so 2 divided by n. That's our delta x. Then f of xi, so the length of each rectangle, we have xi squared. Xi squared, so here, that's what we want to use. We can choose our point. Oh, by the way, when we approximate, when we add up the areas of rectangles, That's called a Riemann sum. So it gets a name. It's called a Riemann sum. So xi, we choose the right endpoint. All right. You know, we have choice. Actually, when we take a limit, it doesn't matter. You know, we choose right endpoint or left endpoint. But anyway, for now, let's choose the right endpoint. So that would be a plus, right? A plus I times delta x, right? Because each width of rectangle is delta x. So the first one will be, so add up all this, we get 2i divided by n. So we put it into the function. So that would be xi would be 2i divided by n. That would be 2i divided by n squared, which is 4i squared divided by n squared. Then we use the summations. We put in the summation, right? We simplify, we get this, a divided by n cubed. Then we summarize I squared from 1 to n. Then a divided by n cubed is just a common factor of each I squared, right? We can use I squared formula, summation of I squared formula. N cubed. Then in the end, we get this. Now we take a limit. So we sum up all the rectangles, the n pieces of rectangles. We sum up the areas of the n pieces of rectangles. We get this. We get like a function, right? Function in terms of n. We get a function in terms of n. Then we use the definition. We take a limit, let n run to infinity. Right? So that's this. That's a limit. N goes to infinity with this summation of the area of the rectangles. Then limit, we can take a limit of each one, right? Well, limit of constant a over 3 is a over 3. A limit of 4 over n when n run to infinity, that's a 0, right? And of course, same thing for limit when n runs to infinity, a divided by 6n squared, that also will be 0. So the area of that is a divided by 3. 4, we don't have the picture. I wish I have a picture of this. Okay, for this integral. So we want to find the integral of this, or the area under function x squared from 0 to 2. Right? Can you imagine the parabola? Right? The upward parabola goes from 0 to 2. You see that? The area under x squared from 0 to 2 is exactly a over 3. So we don't need to approximate anymore. All right. You may choose left point to try yourself. So this example use right endpoint to evaluate the function value. You could choose left endpoint. Then you will see the answer is the same, a over 3. Or you can choose middle point. It doesn't really matter. It's all, in the end, the answer is the same because this is the exact area. Okay, any questions? What is middle left endpoint? When we talk about rectangles, right? Okay, let's look at this picture. So width, we know each width. So we have 4 rectangles here. The width here is b minus a divided by 4. But then we want to find the length of each rectangle. How do we find each length of rectangle? Do we see this function value? But a function value, it depends on the point, x value, right? So f of x depends on x. So choosing x, how many x we have? because this rectangle will have many different axes. So choosing x value, so we have choice of choosing x value to evaluate the function value, f of x. So should we choose A? If we choose A here, the starting point, that's the left endpoint. But we also can choose the right endpoint. Only look at the first rectangle. Look at the first rectangle. We may choose A to evaluate the function as the length of this first rectangle. Or maybe we can choose the red endpoint on this rectangle to be the length of this rectangle, first rectangle. You see the area will be different, right? If we choose the red endpoint, the area will be more than choosing the left endpoint to approximate. Does that answer your question? Okay. But as we were saying, it's not important anymore when this definition is defined. When this definition is defined, the Riemann sum now becomes infinite many pieces. Because Riemann sum used to be n pieces, right? N areas of rectangles. But because we're taking n into infinity, we're coming from finite world to infinite world. So we call it definite integral. So we don't really care because in infinity, you know, the constant term becomes so small, it can be ignored. So it really doesn't matter which point we choose now. We can choose left end point, we choose middle point, we choose right end point, doesn't matter anymore. Okay. Let's see, we have time. Okay. Let's take 5 minutes to do this one, to do checkpoint 1.7. Use a definition, okay? So we want to find the integral, the area under the function 2x minus 1 from 0 to 3. And you see this area, you see this function is a linear function, right? You see that's a rectangle. So this one actually we could use, this one if we want, we can use algebra to find its area. But let's use the definition we just learned. Remember the definition? Let me show you one more time the definition. The integrand is 2x minus 1 in the example. In the exercise, the endpoint is 0 to 3. So from A to B is from 0 to 3. And the integrand, or the f of x, is 2x minus 1. So use this definition to find its area. Then you can check by using algebra. Because f of x, 2x minus 1, is a linear function, right? Linear function you see from 0 to 3, that's a triangle. And we have a formula to find the area of a triangle. You may try both ways.
Can you go back to the question?
Okay. Okay, I'm hoping all of you try this question. So before the first one, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people answered. I have, there are 20 of you here. I would hope to receive 20 answers. Oh, Damon asked a question. Is it really A/3 since you are using limits to? Yeah, that's the miracle of it, Damon. Yes, it's exactly A/3. I would like to encourage you later on to choose different points for the length, right? You will see. If we choose left endpoint, it gives you A/3. You choose a middle point, also gives you A/3. Right? You cannot argue anymore, right? That is exactly A/3. Oh, is the answer 6? Well, right. If you want, you can use. So let me use something else. So I would get x squared minus x. I get a 9. I get 6. 9. 3 squared is 9. 9 minus 3, that's 6. Then evaluate at 0. Is it 6 or 7? Let me get a pen. Oh, I get a different answer. I think it's, however, I'm doing in my head, I get 7. I'm not sure if I'm right. You have to use a power rule. Oh, you could do anti-differentiation, but I haven't talked about the fundamental theorem of calculus yet. But if you know it, you could use it. Any other different answers? So 6. Well, you could draw a picture to 6. All right. Yeah, it is a 6. It is a 6. Because x squared minus x, evaluate at 3, that's 6. So 9 minus 3, that's 6. Good. Good job. Good job. But did you do by the definition? Okay, yes, indeed, it's a 6. All right. Anyone has any questions? Can you show the solution? Okay, let me write here. So basically what I did is I already used the fundamental theorem of calculus. All right, so I anti-differentiate 2x. So anti-differentiate, I get x squared for 2x, right? Anti-differentiate 1, I get x. So after anti-differentiation, I get x squared minus x. Then I evaluate at the endpoints. So when I evaluate at 0, I get nothing, I get 0. When I evaluate at 3, I get 3 squared minus 3, which is 6. Right? I don't want to use, you could try. So basically this is for you to try use the definition, but I don't have that much time. I only have 20 more minutes. I want to finish what I planned to do for today. But I would still encourage you to use this definition, all right? Use this definition, you know, you get a function from here, get a function in terms of n. When you do the summation, you get a function in terms of n. Then you take a limit of that, okay? You take a limit of that, you should get 6. It's too much for me to write on it. Okay, all right, now let's go into fundamental theorem of calculus. All right, this is all about, so that's the important part of this today's lesson, okay, today's lecture. I'm not sure if I have, so fundamental theorem of calculus has 2 parts. Okay, let's talk about this mean value theorem for integrals. So let's say if f of x continues over an interval a to b, then there is at least one point c in AB such that f of c equals to 1 over b minus a of this. This is called mean value theorem. All right. So this will be obvious to draw a picture of it. Let me see if I can find the picture. So that's why I posted the other book, which is James Stewart's Essential Calculus. It's like a very classic calculus textbook. So check there. I think they have a picture about this, because this can be pictured. Or this formula can be written in this way. The integral f of x from a to b equals to f of c times b minus a. So we can use that mean value theorem to find the average value of a function. Let's see this example. But we want to find the average value of function for f of x equals to a minus 2x over the interval from 0 to 4. And find c such that f of c equals to the average value of the function in the interval. So the formula states the mean value theorem given by this: 1 over b minus a, b is 4, a is 0. The integrate from 0 to 4 of the integrand is a minus 2x dx. Then when we do this, we get half 4 times a equals to 16. Oh, again, you see this integrand? The integrand is a line, right? It's a straight line. A straight line will form a rectangle in the integral, in the lower limit, upper limit 0 to 4. In the interval of 0 to 4, right? There will be a triangle. So triangle, we can do half times the base times height. So we're going to have, the base will be 4, because 4 minus 0 will be 4. The height is 8. Well, we can find that equals 16. By using mean value theorem, we should also get 16. Then we use this one, because we want to find such c, right? Such c, you can use this one. So that means a quarter of 16 equals to 4, because the area is 16, right? So 1 over 4 minus 0, that is 1/4. 1/4 of the area is 4, so that means a minus 2c is 4, right? So what's the f of c? We want to find f of c. Then, see, solve this. Solve this, so c equals to 2, right? Oh, the picture is here. Good. The picture is here. So this is one example to verify the, to apply the theorem, mean value theorem. Okay, anyone has any questions? All right, let's go to fundamental theorem of calculus. Let me see if I, yeah, this is all about average value. Okay, fundamental theorem of calculus, part 1. F of x is continuous over the interval a and b. And the function f of x is defined, the big F of x is defined as the integral of this. Let's check this. The lower limit is a. Right? The lower limit is a. And the upper limit is not b, it's x. It's x. Okay, so f of x. Right? In capital letter F, x is a variable. So in the integration sign, that's from a constant number to x. Then f of t dt. Okay, f of t dt. Don't even ask why for now. Just remember this. And then, if this, then the derivative of f of x is the capital letter of f of x is exactly the lowercase f of x. All right? Over the interval AB. Everything is in the interval. So, all we need is a function, the integrand is continuous on the integral, right? On the integral. And we can write this in another way. We can write f prime of x equals to d f dx, right? With this. Let me see if I can find another way of writing it. Okay, let's just stare at this for a moment to see if anyone has any questions. So capital letter f of x equals to integral of lower limit a, upper limit x, f of t dt. All right. You see b doesn't show in this equation. But the x has to be in between of a and b. So x is a value inside the interval a and b. Right, so this should be another condition. This x is inside a and b, a to b, in the interval a to b. So this is proof, right? I'm not going to go over this proof because this course we don't care about the proofs. We just use any theorem for granted. Use mean value theorem to prove. Okay, let's see this one. Let's see one example. Finding a derivative with the fundamental theorem of calculus. Use part 1 to find the derivative of g of x. Now we want to find a g prime of x. Well, what's g prime of x? Let's check this. The lower limit is 1. Is 1 in the domain of the integrand? Yes, right? If we plug in 1 into t, we get a 1 over 1 plus 1, 1/2. So that's okay. So 1 is in the domain of the integrand. So that's fine. So 1 up to x. Well, 1 up to x. So constant up to x. Then the g prime of x is just equals to inside, so changing t to be x. So g prime of x equals to 1 over x cubed plus 1. Okay. That's it. So by fundamental theorem of calculus. That's it, right here. So if this is the case, right? If capital letter f of x equals to integrate integral from a to x, and a is in the interval of, or in the domain of f of t, then f prime, derivative of capital letter F, it's just the integrand. Just the integrand. So the derivative of capital letter F is just the integrand, the lower letter f of x, changing t to be x. Anyone has any questions? Okay, so very easy and convenient formula. So this example, right, g prime of x just equals the integrand, but changing t, the dummy variable, to be x. Well, let's see this one. This one, of course, g prime of r is the square root of r squared plus 4, right? Because 0 is the domain of the integrand. But if we plug a 0 in, we'll have square root of 0 plus 4. It's a square root of 4 with the 2. That's fine. That's how we check the constant, the lower limit. The lower limit has to be in the domain of the integrand. Are we going over all of chapter 1? Not today. Not today, but gradually. So the important part for today is just this fundamental theorem of calculus. Okay, but we need to know, where does this come from? We need to know, where does the integral come from? The integral comes from Riemann sum, right? Riemann sum is in a finite world. Just add up, just add up n pieces, n areas of rectangles. Just add up areas of n rectangles. But the integral is pushing the finite world into infinite world by using the limit idea. By taking n is a finite number, but now we use the limit idea, let n run into infinity. So we define the integral. Integral is in infinite world. What if the lower limit were not in the integral, were not in the domain, you mean, Darren, right? Then we won't be able to use the theorem. Then we won't be able to use the theorem. We have to do something else. We have to change a little bit. So the lower limit has to be in the lower limit has to be in the domain of the integrand for now. Okay, now let's see this one. Okay, let's see this one. This one I want to use fundamental theorem and the chain rule to calculate the derivatives. So capital letter f of x is defined as this. The integrand is sine t. Well, let's check the lower limit. The lower limit is 1. Well, sine 1, so 1 is in the domain of sine t. That's fine. But what about the upper limit? Upper limit, we need to have x to use for the fundamental theorem of calculus. But here we have square root of x. So what do? We use u substitution. We say, okay, let u of x be square root of x. Then we need to find the du. Or what's du? So when we use the fundamental theorem of calculus, if we change that one to be u, then we have to change a dx to be du, right? Or here, right, sine t dt. So we have this square root of x. So we just have to use the chain rule, all right? That's the only thing. That's the only difference. So first one, we check the lower limit. If the lower limit in the domain of the integrand, then we check the upper limit, right? If it's not only x, we just have to attach chain rule to it. So what do? We have sine of u of x is square root of x, then multiply by du dx. What's du dx? The half of 1 over square root of x, right? So in the end, we've got sine square root of x and 2 square root of x. Okay, anyone has any questions? So when the upper limit is not only x, because the dx is just 1, right? It's 1. That's why we don't have, but if that's not x, but something else is a other function of x, we have to attach chain rule, multiply by chain rule. And that's it. Let's see this one. Okay. All right. Actually, we have a couple minutes. Let's finish it. So all of you try this one. Try checkpoint 1.17. Next class, we'll talk about the second part of fundamental theorem of calculus. Can you review how do u dx compute? Oh, okay. Right. For some of you, if you finished, you try this one. Lower limit is 1, upper limit is x cubed. The integral is cosine t. All right. And how do we take derivative of square root of x? That's x raised by half, right? Square root of x. Are you going to upload recording to Blackboard? It is there, James. I'll show you later if you cannot find it. I'll show you where to find the recordings. All right. The good thing to use this CUNY Blackboard is it records and you know, it stays there. Let's talk about square root of x. So square root of x. So equals to, remember x raised by half. Then when we take a derivative of that, just by power rule, get a half of x raised by 1 minus half, right? Attendance, no, not taken automatically. I took a picture. I check your in on my attendance book. Then we get a half x raised by negative half, right? What's that? That's just 1 over square root of x, isn't it? That's how we take derivatives, right? Okay, anybody has answer for this 1.17? You're welcome. Yeah, always ask questions. So we want to find f prime of x. So we check the lower limit. Lower limit is 1, it's fine. It's in the domain of cosine. That means f prime of x equals cosine x. But then we check the upper limit. The upper limit is x cubed. So what is the derivative of x cubed? That's 3x squared. So that means f prime of x equals 3x squared times cosine x cubed. Okay, any questions? So there are two important things to remember for today. The first one is the definition of definite integral. All right, definite integral. Right, this one. So we really need to understand this beautiful equation, right? This beautiful equation. So the section 1 is all about the summation sign, right? The summation, how to approximate the areas of the rectangles. Then the beauty comes from we take the limit, we let the n run into infinity. So we come from the finite world to infinite world. Now we define the integral. The integral is about, you know, dealing with the stuff in infinite world. And then the second part is the fundamental theorem of calculus, part 1. Okay, remember this formula. Remember Remember this definition. Remember this. Okay, remember this one. For anything, if you want to remember, my suggestion is try homework, try exercise, and also write down the definition, you know, several times until your brain register in your brain. Because you know, anything you want to remember, you have to you know, keep trying to remember them, right? Write down a couple of times. And the homework will be, let me assign you some homework. And next time, next class, I'm gonna call people. Okay, homework. 140, 140A. 140A, 149. 150. Okay, let's see. So 140A up to 157. Actually, you know what? Up to 159. Okay, 140A up to 159. Let me write in the chat. So homework 140A up to 159. So good exercise. They're from the textbook. They're from the textbook on my open math. Okay, from the textbook on my open math. All right, anyone has any questions? If not, I'll see you on Thursday, okay?
Professor, I have a question.
Yes.
So when are you going to post this video?
Oh, okay, let me show you how to get the video.
Okay.
Let me stop this now.